427 days into what was meant to be a 30-day mission, the dream of flight on Mars had transformed into something else entirely: a battle against time, nature, and silence. Nearly 297 million kilometers away from Earth on the cold, dusty surface of Mars, a tiny aircraft named Ingenuity clings to existence. Weighing just 1.8 kilograms, this experimental helicopter isn't made from some futuristic alien alloy or a secret NASA prototype. It's a patchwork of familiar parts you might find in your own home: an Android smartphone processor, off-the-shelf carbon fiber components, solar panels, and batteries like those in your cordless drill. And yet, against all expectations, it was flying not just once, but again and again. But now, something has changed. The Martian winter looms, and with it comes the deadly cold. Each night, temperatures on Mars can plunge to a brutal -85 degrees Celsius. As the planet orbits farther from the sun, its already dim sky grows darker. Dust storms become more frequent and more violent, filling the atmosphere with choking particles that block what little sunlight remains. Solar panels can't charge. Instruments freeze. Communication falters. On Sol 427 Martian Day 427, NASA's Jet Propulsion Laboratory in Southern California tries to contact Ingenuity, just like they had every day. But this time, there's no response. Silence. They try again. Still nothing. The team gathers, exchanging glances heavy with unspoken fear. The signs are not promising. Has Ingenuity finally succumbed to the harshness of Mars? They don't want to give up just yet. There's one last hope. A final attempt to re-establish contact. One final trick to call out across the void. 6 years earlier, back on Earth, no one really believed this day would even be possible. In fact, many didn't believe Ingenuity deserved to go to Mars in the first place. When I visited JPL in Pasadena during the early development phase, the helicopter sat quietly on a lab bench, unassuming, fragile, and completely out of place among the massive robotics and high-tech instruments destined for Mars. Even within NASA, the project faced resistance. Dr. Kenneth Farley, the lead project scientist for the Mars 2020 Perseverance rover, was candid. "I've personally been opposed to it," he admitted at the time. Spending 30 days working on a technology demonstration does not directly further the goals of the science mission. In bureaucratic terms, it was seen as a diversion, a toy project. A risky, unnecessary distraction. After all, space missions to Mars typically run into the billions of dollars. Ingenuity had a budget of just $80 million less than the cost of Ridley Scott's film The Martian. But that's where the magic of Ingenuity truly began. What this tiny team lacked in budget, they made up for with grit, creativity, and raw belief in an audacious idea: that humans could one day fly on another world. And they were right. February 18, 2021. The Perseverance rover screams through the thin Martian atmosphere, surviving a harrowing descent to land safely on the red surface. Attached to its underbelly, nestled in a protective shell, is Ingenuity. On that day, Sol 0, the first day of Mars surface operations, the umbilical cord is severed. The rover and the helicopter go their separate ways. Ingenuity's mission is a simple, bold one: prove that powered, controlled flight is possible on another planet. But this is no ordinary challenge. Mars' atmosphere is just 1% the density of Earth's. It's thinner than what you'd find at the edge of Earth's stratosphere. To lift off the ground, Ingenuity must weigh almost nothing, and its rotors must spin at a dizzying 2,400 RPM, 5 times faster than a helicopter on Earth. For weeks, engineers meticulously run through system checks, spinning the rotors, testing navigation algorithms, checking onboard systems. Every subsystem must be verified, every risk mitigated. The Martian environment does not forgive mistakes. Then, on Sol 58, they decide she's ready. The rotors spin. Dust kicks up. And for a brief, glorious moment, history is made. Just 117 years after the Wright brothers flew the first powered aircraft on Earth, humanity takes flight on another world. The team is ecstatic. Over the next few weeks, Ingenuity performs 5 flawless flights. She rises, hovers, darts, lands. With each new flight, confidence grows. What was once considered an impossible dream is now a reality. Mission accomplished. The tech demo is officially over. Time to pack it up. Or so they thought. But something unexpected happened: success. And with success comes opportunity. NASA, now paying close attention, asks the team to keep going. Ingenuity's mission is extended. Her new role: act as a scout for Perseverance, flying ahead to identify points of interest, paths of least resistance, and dangerous terrain. The helicopter becomes a critical asset in the hunt for signs of ancient microbial life on Mars. But there's a problem. This new mission was never part of the original plan. The team had no protocols, no infrastructure, no playbook for prolonged flight operations on Mars. After all, Ingenuity wasn't even supposed to survive this long. "We were thrown into the deep end of the pool," one engineer remarked. "We didn't have procedures for this." Until that point, every flight had been planned with extreme caution, launched from well-mapped locations chosen by satellite data and confirmed by Perseverance. But now, they were venturing into the unknown. What happens next would define the legacy of Ingenuity. We're tested hundreds of times in JPL's wind tunnel and tens of thousands of times in simulation, but now that they have to keep up with the rover they're flying. Into the unknown now. Flying the helicopter isn't easy. At its closest, Mars is 56 million kilometers from Earth, which means there's at least a 6-minute round-trip communications time delay, which is way longer than Ingenuity 2-minute maximum flight time, so she has to fly autonomously. So what happens is the pilot programs in a route and Jenny does the rest. But to start, JPL first needs to know exactly where she's located. You might think that they would use GPS, but for GPS to work on Earth, you need at least 24 satellites for full coverage. And around Mars, there are only 7 satellites total, so Ingenuity can't use this method. So instead, what she does is far simpler. We have 2 cameras, a forward-facing 13-megapixel camera, and then the one pointing down is the one that we use to navigate. The navigation camera takes 30 black and white images per second. Inu's computer analyzes the image and identifies features on the surface. You can think of it sort of like an optical mouse. Like your optical mouse is on the mouse pad, it doesn't know where on the mouse pad it is, but when you move to the right, it knows you move to the right, because what it's doing is it's looking at features on the surface of the mouse pad and watching them move under its field of view. So Ingenuity is essentially doing the same thing. It's looking at the surface, it's picking out features like rocks and other things, and between camera images is it says, oh, this rock moved this way, this thing over here moved this way, and from that you can compute a transform to say my helicopter was here and now it's here. Relative to the image. Now this sounds good, but the method isn't 100% reliable. On Flight 6, the first time she leaves her testing area, Ingenuity detects an error. 54 seconds into the flight, she starts wobbling wildly, tilting 20 degrees at a time her emergency alarms blare. Applause. We had black and white image, black and white image, black and white image, and we had a color image come very closely to where that black and white image occurred in time. This color camera was added late in development, leaving little time for testing, and during this flight, one of the images arrives at the exact same moment as a black and white image. The system doesn't know what to do, so it drops the black and white image. This makes every following image one step behind. This means Ingenuity cameras are giving her outdated information, so even when she's in the right spot, the computer thinks she's lagging behind and pushes her forward, so she overshoots, tilts too far, and then has to overcorrect in the other direction. This cycle repeats, making her wobble worse in a positive feedback loop. Now that is a problem, but it isn't fatal. The desensing issue was like one camera frame off. If it had been more than that, I think you could imagine that it might have death spiral. Instead, Jenny detects the problem and is able to emergency land before it gets too ugly. While safely on the ground, JPL discovers the error and quickly corrects it with a software patch. It's a close call, but they recover. Over the next dozen flights, they keep up with the rover and support the mission that is until flight. Music 19. We were about to fly that 19th flight, and I got a phone call the afternoon before, basically saying there's a dust storm brewing, a near-zero crater, so we quickly cancel the flight, and so, well, we're just going to hunker down and see what happens. They brace for impact. It lasts 6 days with winds gusting up to 20 m/second. That first dust storm in the middle of fall in the first First Martian year that we're on the surface, it clobbered us, but they make it through nervously. They try to make contact, and she survived. She hasn't died or toppled over, but now they have a new problem. Dust on Mars is no joke. For Ginny, there are two big problems. First, dust is covering her solar panels, reducing power by 18%, and second, it's clogging her mechanical components. We went to go fly, and when we went to wiggle the servos, they were actually stuck. They were kind of jammed from the dust, so that aborted the first attempt at Flight 19. Now, JPL had anticipated both of these problems, but they hadn't had the time or budget to fix them, so for the first, they just have to accept that they have reduced solar power, and they adjust their flight durations accordingly. For the second, they find a workaround by repeatedly wiggling the servos until the joints clear, so she's able to keep flying, albeit wounded, and survival isn't getting any easier. See, every Martian night the temperature drops precipitously. My friend Alex from the channel Astrum describes it well. With less atmosphere, M became far worse at retaining heat when the surface back on Earth. Inside JPL's wind tunnels, Ingenuity's flight systems had been tested hundreds of times under simulated Martian conditions. In digital simulations, she had flown tens of thousands more. But no simulation could fully prepare her or the team for what came next. Ingenuity's role had changed. She was no longer just a demo. She now had to keep pace with Perseverance, traversing an alien landscape filled with unpredictable obstacles. And that meant leaving behind the carefully prepared test zones and flying into terrain never studied from orbit, truly into the unknown. But flying a helicopter on Mars is no small feat. The physical distance alone makes it a challenge unlike anything attempted before. Mars, at its closest approach, is still 56 million kilometers away from Earth. That means a one-way signal from Earth to Mars takes at least 3 minutes. Round trip? Over 6 minutes. That's far longer than Ingenuity's average flight duration, just 90 to 120 seconds. So how do you fly something you can't remotely control in real time? You don't. Ingenuity must fly autonomously. The JPL engineers program in a flight plan ahead of time a set of waypoints, altitude targets, and orientation instructions. Then, once the command is sent, it's entirely up to Ingenuity. She must sense, think, and act all on her own while in the air. But in order to fly autonomously, she first needs to know where she is. You might assume she uses GPS after all. It's how we navigate on Earth. But GPS needs a constellation of satellites in orbit to triangulate a device's location. On Earth, we rely on over 30 satellites for full global coverage. Mars? It only has 7 orbiters, none of which are equipped for GPS functionality. So Ingenuity relies on something far more analog and surprisingly elegant. She uses vision. Equipped with 2 cameras, a forward-facing 13-megapixel color camera and a downward-facing black and white navigation camera, Ingenuity watches the Martian terrain below her. The navigation camera takes 30 grayscale images per second, and her onboard computer analyzes these images in real time to detect surface features, rocks, shadows, soil patterns. Think of it like an optical mouse. Your mouse doesn't know where it is on your desk, but it can detect relative movement by comparing the texture of the surface beneath it from moment to moment. If that texture moves slightly left, it knows you've moved left. Ingenuity uses the same principle. By tracking how these features shift frame by frame, she calculates her movement through space. It's simple, it's brilliant, and most of the time it works. But on Flight 6, things go wrong. For the first time, Ingenuity leaves the safety of her pre-surveyed test zone. She's heading into an uncharted area, and just 54 seconds into the flight, something strange happens. She starts to wobble. Badly. Her frame begins to oscillate, tilting erratically, sometimes by as much as 20 degrees. Emergency alarms sound inside her processor. Something is off. Back at JPL, the team examines the telemetry. They discover the cause, a desynchronization between camera frames. A color image taken by the forward-facing camera was captured at almost the exact same moment as a navigation image. But due to the way the software was written, it wasn't expecting both images at the same time. So it drops one. The result? Every navigation frame afterward is now one step behind reality. Ingenuity thinks she's lagging behind her expected path. So she pushes forward. But because she's actually not behind, she overshoots. Then she corrects. Then she overshoots again. This creates a vicious cycle, a positive feedback loop of error correction that magnifies itself. She's flying blind with a half-second delay. In engineering terms, this is a nightmare scenario. But Ingenuity holds on. She detects the fault and initiates an emergency landing sequence, putting herself down safely before things spiral out of control. It could have been catastrophic, but it wasn't. JPL quickly patches the software, fixing the synchronization bug. The lesson is clear. Every line of code matters on Mars. In the following months, Ingenuity flies again. And again. And again. More than a dozen flights in total. She scouts ahead of Perseverance, mapping terrain and helping engineers choose optimal driving paths, sometimes even detecting hazards that could have trapped or damaged the rover. And then, just before Flight 19, they get a call. There's a storm coming. The Martian dust storm begins to build near Jezero crater, the landing site of Perseverance and home to Ingenuity. Within hours, high winds and thick dust engulf the region. JPL cancels the flight and prepares for the worst. For 6 Martian days, the storm rages. Winds gust up to 20 meters per second, strong enough to erode rock and potentially damage equipment. When the dust finally settles, the team anxiously attempts to reconnect. She's still there, still standing, still alive. But now they face 2 new challenges. First, dust on her solar panels. The Martian atmosphere is dry and filled with ultrafine particles. Without rain or wind strong enough to clear them, solar panels get covered quickly. For Ingenuity, this meant an 18% drop in power output. Less energy means shorter flights, longer recharge cycles, and more time spent idle. Second, jam servos. The fine dust had infiltrated her moving parts. When they attempted to test her joints, the actuators that control blade pitched the servos stuck. They were clogged. The flight was aborted. While these issues had been anticipated during development, there was never time or funding to fully solve them. So, the team improvised. For the power loss, they adjusted their flight plans to use less energy. For the jammed servos, they developed a technique, repeatedly wiggling the components until the dust cleared itself out. Crude but effective. Ingenuity was flying again. Wounded but flying. And her challenges were far from over. Because Mars with its paper-thin atmosphere does a terrible job retaining heat. Every Martian night, as the sun dips below the horizon, temperatures plunge by over 100 degrees Celsius. Without insulation, internal components risk freezing. Batteries lose capacity. Circuits can crack. Survival on Mars isn't just a triumph of engineering, it's a daily act of resilience. In the brutal Martian cold, where temperatures plummet each night, Ingenuity's fragile internals are barely kept alive. Her warm electronics box, a kind of high-tech thermal sleeping bag, was only designed to protect systems down to minus 45 degrees Celsius. But on Mars, during the dead of winter, the chill dives far lower. For days and nights on end, Ingenuity is exposed to full freezing. And she survives. Well, almost. One component doesn't make it. The inclinometer is dead. The inclinometer is a critical piece of hardware. It's what tells Ingenuity how she's oriented in 3D space before takeoff, her initial roll, pitch, and yaw. In essence, it's how she knows which way she's pointing. Without it, she's flying blind. You might think 10 degrees off in heading isn't a big deal until you realize that on Mars, that could be the difference between skimming over a rock field or smashing into a mountain wall. Without orientation, autonomous flight is impossible. For a moment, the team at JPL is stunned. This could be the end. But then a spark of inspiration. After all, Ingenuity was built from off-the-shelf consumer technology. Literally. Her processor came from a Samsung Galaxy S5. Her sensors? From a Google Pixel 3. If you've ever held a smartphone, you've held a piece of Ingenuity. And smartphones, as we know, don't use inclinometers to detect orientation. They use something else. Inside every modern phone are tiny micro-electromechanical systems, MEMS. These are your accelerometers and gyroscopes. Each sensor is made up of microscopic suspended masses attached to flexible arms like tiny springs. When a phone is tilted or moved, these masses shift, ever so slightly. And by tracking that shift through changes in electrical capacitance, we can infer motion, acceleration, and orientation. It's Hooke's law and Newton's second law in action. F equals kx and F equals ma become A equals kx slash m. Connecting acceleration to displacement at microscopic scales. The suspended mass forms part of a capacitor. As the distance between the plates changes, the capacitance changes, and so, engineers can measure motion in the x, y, and z axes. This is how your phone knows when to rotate the screen, track your steps, or detect freefall. Add a gyroscope, and you have an inertial measurement unit or IMU capable of tracking motion and orientation. And Ingenuity has the same IMU as the Google Pixel 3. So the team rethinks the problem. The inclinometer only tells them initial orientation before flight, not during. But the IMU, if calibrated correctly, can do something similar. So JPL rewrites the code. They reprogram Ingenuity's computer to use the IMU to simulate the function of the dead inclinometer. It's risky, but it works. We got lucky, one engineer admits. If we had to lose any single component, the inclinometer was probably the only one we could afford to. But luck only goes so far. There's another lurking threat. And it's invisible. Cosmic rays. Unlike Earth, Mars has almost no magnetic field and only a wisp of atmosphere, which means the surface is bombarded by high-energy particles from deep space. One cosmic ray 1 particle is enough to flip a bit in computer memory. A 0 becomes a 1. These bit flips can wreak havoc. In 2003, a cosmic ray in Belgium famously added over 4,000 fake votes to a candidate in an election. And in a Martian helicopter flying autonomously, a flipped bit at the wrong moment could mean catastrophe. That's why most spacecraft use radiation-hardened processors built from the ground up to withstand cosmic radiation. But Ingenuity doesn't have that luxury. Her processor is a stock smartphone chip. So why hasn't she crashed? Because, as it turns out, consumer-grade tech is tougher than we thought. JPL ran radiation tests on different batches of chips. Most failed. Some didn't. But one particular processor, for reasons still not fully understood, proved highly resilient. Instead of spending millions designing a custom chip, the team simply selected the off-the-shelf part that consistently survived the worst cosmic rays they could throw at it. And it worked. Sometimes space doesn't need perfection. It needs creativity. Against the odds, Ingenuity survives the Martian winter. Barely. She stays within communication range of Perseverance, just enough to get commands and send data. And when spring finally comes, it's like Mars breathes again. With longer days and brighter skies, solar power surges. Ingenuity fully recharges. She's back. Over the next 41 flights, she explores areas the Perseverance rover could never reach: craters, ridgelines, and fractured terrain. She captures sweeping views of the Martian horizon and collects high-resolution images that inform the rover's route. But Ingenuity isn't just surviving. She's thriving. JPL begins pushing the limits. They want to fly farther, faster, higher. But there's a problem. The faster she flies, the faster the ground features blur beneath her. And her vision navigation system, the same one that uses that downward-facing camera to track motion, can't keep up with fast motion close to the surface. So, they adapt. Fly higher. By increasing altitude from the original 10 meters to 24 meters, the team widens her field of view. Ground features appear to move slower, even if she's flying faster. And it works. She goes from 2 meters per second to 10 meters per second. Setting speed records, altitude records, distance records. Ingenuity begins to redefine what flight on Mars looks like. A once-in-a-lifetime experiment has become a full-fledged exploration tool. Now, after over 70 flights, Ingenuity and Perseverance make it to Neretva, an ancient Martian river delta in Jezero crater, a region rich with geological history, possibly one of the most promising places to search for signs of ancient life. Every day, Ingenuity flies missions, capturing hundreds of high-resolution images. And every day, she sends them back to Earth. She's not alone. Perseverance does the same, including selfies where both robots are in frame, pioneers of a new chapter in exploration. Honestly, they've become the most online duo on Mars. Perseverance and Ingenuity always active, always transmitting, always sharing. We know where they are, what they're doing, and what they've seen. The endless stream of Martian selfies, terrain scans, and aerial shots feels oddly familiar, not unlike us, humans, constantly connected, endlessly uploading. But there's a difference. For us, that data lives in marketing databases, sold and traded behind the scenes. For them, every byte is archived by NASA, a time capsule of interplanetary exploration. Yet even on Mars, privacy and control over data echo our digital lives, reminding us just how far and how close technology brings us. Thanks to today's sponsor. You can skip this sponsor segment if rewriting for a non-commercial format. Now, back to the red planet. With the Martian spring warming the surface, the team had one more challenge left: cross a stretch of dunes and reach Bright Angel, the next rendezvous point with Perseverance. Flight 71. It begins as expected. Ingenuity lifts off, blades spinning, ascending over the soft, shifting sands. But just 10 seconds in, her navigation begins to fail. The helicopter suddenly initiates an emergency landing. She comes down hard. The team pings her. She's still alive. They scan the error codes. The problem becomes clear. As she flew over the dunes, there weren't enough distinct visual features, no rocks, ridges, or textured shadows. Her vision system lost track of movement. Without landmarks, Ingenuity couldn't tell where she was. This wasn't new. It was the same root cause as the near disaster on Flight 6. But unlike that earlier flight, there's no clever software patch this time. It's a limitation of the terrain itself. They inspect her. No visible damage. So they decide on one more flight. A simple test. Straight up. Take a panoramic scan. Come straight back down. Flight 72. She launches. Lifts. Scans. But on the descent, it happens again. This time, the landing is fatal. Perseverance drives over and captures the image. There, lying still, is Ingenuity. Her rotor blades shattered. Her body intact. Her mission over. When we saw that image, one engineer said, "When we saw the blades broken, it was heartbreaking." Because Flight 71 had also ended in an emergency landing and they'd gotten away with it. No damage. Just luck. But this time, luck ran out. It's the first ever air crash investigation on another planet. The first interplanetary aircraft, and now the first aviation accident in the history of Mars. They examine the crash site. Something odd stands out. The rotor blades are broken, but the ground doesn't show the damage you'd expect. With blades spinning at high speed, any ground strike should have sprayed carbon fiber shrapnel in a clear radial pattern. There should be gouges, impact marks, even visible signs from orbit. But there's none of that. So what happened? To answer that, they returned to the lab, to the prototype blades. They're feather-light carbon fiber composites with a foam core. Incredibly strong for their weight, but also extremely thin. As the blades spin, the tips trace out a large circle like a hula hoop in motion. You might expect that if a force lifts one side of the rotor, the helicopter would tilt immediately in that direction. But that's not what actually happens. Because the blades are in motion, physics adds a twist. The phenomenon is called precession. When a force is applied to a rotating object, the resulting tilt doesn't occur where the force was applied. Instead, the maximum effect shows up 90 degrees later in the direction of rotation. This is why a spinning bicycle wheel, when torqued in one direction, responds in an entirely different direction. It's unintuitive, but essential to how gyroscopes and helicopters work. Ingenuity uses two sets of blades, rotating in opposite directions. This cancels out the overall torque, keeping the craft stable. But each individual blade still experiences precession and flexes accordingly. This repeated stress focuses on a single critical zone, the transition point where the reinforced root of the blade tapers into the flexible span. And sure enough, when they look at the crash photos, that's exactly where the blade snapped a jagged fracture right at the taper. So here's what happened. As Ingenuity descended from Flight 72, She hit a slope, a dune, uneven and soft. The angle of impact transmitted force up through the body, generating a sudden precession torque. The blades, still spinning at high speed, flexed under the strain. They didn't strike the ground. They tore themselves apart under their own momentum. It wasn't the avionics. It wasn't the servos. It wasn't the software. It was just physics. And so, the first aircraft on another planet met its end not with a dramatic crash, but with a quiet, graceful failure. But what a legacy. Originally designed for just 5 flights, 30 days. She flew 72 times. For over 1,000 days. She proved powered flight is possible in the thin Martian air. She scouted terrain for a $1 billion rover. She captured hundreds of images and inspired thousands of engineers. She became the first Martian pilot, a symbol of human ingenuity in the most literal sense. And though she now lies still in the sands of Jezero crater, her mission isn't over. Because the data she sent back, the lessons she taught, the doors she opened, they will fly again. So what comes next? What do you build after sending the first helicopter to Mars and watching it exceed expectations by a factor of 14? You build Chopper. That's the working name for the next generation Martian rotorcraft. And if Ingenuity was a prototype, Chopper is evolution. Bigger, smarter, stronger, capable of doing science on its own. Earlier, you held the original Ingenuity blade, that delicate feather of carbon fiber and foam. Now, meet the next-gen blade. At first glance, it looks similar, but look closer, and you'll see the subtle reinforcements. The new design accounts for the stress of precession torque and hard landings. These blades are tougher, engineered to withstand the kinds of forces that shattered Ingenuity's rotors on Flight 72. But the biggest change? There are 6 rotors now instead of 2. A tri-blade configuration, duplicated and balanced for control. It's not just for redundancy or stability, it's for capacity. With 6 rotors, Chopper can carry more weight, including its own scientific payload. For the first time, a Mars helicopter won't just be a scout. It will be a scientist. And with this new platform comes another game-changer, a custom-designed, ultra-lightweight radio system capable of communicating directly with Mars orbiters. Ingenuity had to stay close to Perseverance to relay messages. But Chopper? It's a free bird. It can fly independently across valleys, craters, dunes, and cliffs. No need to stay within line of sight of a rover. No more tethered missions. Inside the sleek blue payload box beneath Chopper, there's room for up to 5 kilograms of scientific instrument sensors, imagers, even sampling tools. That may not sound like much, but on Mars, that's enough to run full planetary investigations, deploy instruments, or inspect terrain no rover could ever safely reach. And it moves fast. In just a few minutes, Chopper can travel 3 kilometers per solar feet that would take a rover days or even weeks. Suddenly, inaccessible geology becomes reachable. Exploration becomes dynamic. And that's generating huge excitement in the scientific community. What you see today is a 5th-scale prototype, a proof of concept. But it's just the beginning. The design is modular. On top, the flight vehicle Chopper itself. Below, a mid-air deployment platform. Why? Because helicopters don't need complex sky cranes like rovers do. They just need a launch pad. So here's the vision. A spacecraft descends through Mars' atmosphere. Rockets slow the fall. At a precise moment, Chopper detaches midair, fires its rotors, and flies itself to the surface, a graceful touchdown under its own control. 3, 2, 1, liftoff. A new age of flight on Mars is coming. And yes, one day, there may be airports on Mars. A fleet of aircraft. Some like Ingenuity, others like Chopper, and some even larger. These flying machines could work in swarms, rapidly surveying terrain, monitoring weather, or serving as transport. All of it sparked by a tiny 1.8-kilogram drone NASA didn't even believe in at first. Back when Ingenuity was just an idea, many scientists called it a distraction, a gimmick, a toy. Flying on Mars? Come on, they said. It sounded like a backyard inventor's fantasy, something you'd see on YouTube, not on a $1 billion interplanetary mission. But then she flew, and the paradigm shifted. It's like 1890 again. When someone said, "I'm going to fly," and everyone left. That kooky guy in his garage is going to get himself killed. Then came the Wright brothers. Then came Kitty Hawk. And now Mars. In fact, there's a piece of that legacy still flying. Tucked beneath Ingenuity's belly is a tiny square of fabric, 1 square centimeter of muslin cloth, cut from the lower left wing of the original Wright Flyer. The first airplane on Earth, carried on the first aircraft to fly on another planet. A direct line from Kitty Hawk to Jezero Crater. But here's the twist. Despite everything, the crash, the broken blades, Ingenuity isn't entirely dead. She's still taking weather readings. Still snapping images. Still sending back data every day. Long after her flight mission ended, she continues to serve as the first weather station with wings on Mars. And that's extraordinary. She was only supposed to fly 5 times. She flew 72. She was never meant to survive one Martian winter. She lived through 3. And even after a fatal crash, she refused to stay silent. The team couldn't be prouder. Not just because of how long she lasted, but because of what she started. This is only the beginning.